Professor Yu, we can start now.
Okay. Good morning, everyone, and welcome to the live broadcast by AP Advanced Photonics Nexus. And today we have the pleasure of inviting Professor Saif Islam to give us the talk. Before we start, I would like to briefly introduce the sister journals of Advanced Photonics and Advanced Photonics Nexus. Advanced Photonics is a journal that the co-editors-in-chief are Professor Larry Yuan and Professor Anatoly Zayats. And AP is really publishing the cutting-edge papers in optics and photonics, often published by leaders in the field. So in 2023, the Advanced Photonics have received a impact factor of 20.6 and is the equal number 3 together with light science and applications in all the optics journals. AP Nexus, Advanced Photonics Nexus, on the other hand, is the sister journal of Advanced Photonics, and it is also indexed in ESCI and is open for submission. And also those manuscripts that are rejected by Advanced Photonics but are of a good quality, we would also suggest the authors to be to transfer to Advanced Photonics Nexus. It is also an open access journal. Again, the editors-in-chief are Professor Larry Yuan, Professor Anatoly Zayats, and also Professor Chen Weibiao. And it has an editorial board membership of 38 leading researchers from across the world. And it accepts submissions of subjects throughout the field of optics and photonics. So also between Advanced Photonics and Advanced Photonics Nexus, we also organize theme issues. For example, in 2022, we published a theme issue on photonics with thin film lithium niobate, which was very well received. In 2023, we published a theme issue in optical orbital angular momentum, and to celebrate the 30th anniversary of the confirmation of orbital angular momentum. And this year, the theme issue in progress is about artificial intelligence and photonics. So we would welcome all everyone to submit to these theme issues. So once again, and this is a very brief introduction of Advanced Photonics and Advanced Photonics Nexus, and we hope that you find these journals helpful and attractive, and also we would like you to submit your best works. So about today's talk, we are honored to have Professor Saif Islam, who is a professor of electrical and computer engineering at UC Davis. And so he also serves as the director of the Center for Information Technology Research in the interest of society at UC Davis. He obtained his B.Sc degree from Middle East Technical University in Ankara and the MS degree from Bilkent University, both, of course, in Turkey, and the Ph.D. degree in electrical engineering from UCLA in 2001. And He has published over 300 scientific publications and 42 patents. And his research focuses on semiconductor for ultrafast optoelectronics, nanoscale transistors, nanosensors for AI-enabled imaging, and wide bandgap semiconductor materials and devices for harsh environment applications. He received the NSF CAREER Award, Outstanding Research Faculty Award of UC Davis Engineering, IEEE Professor of the Year, and the UC Davis Academic Senate Distinguished Teaching Award, and SPIE's Aden and Marjorie Meinel Technology Achievement Award. He has organized 36 conferences and is a fellow of AAAS, Optica, SPIE, IEEE, and the National Academy of Inventors. So let's welcome Professor Saif Islam to give a talk on the work around the work he published recently on the cover of the Volume 2 and Issue 5 of Advanced Photonics Nexus, which is about achieving higher photo absorption than Group 3-5 semiconductors in ultrafast thin silicon photodetectors with integrated photon trapping surface structures. So I will stop my screen share and give the screen to Professor Islam.
Is my screen visible to you all?
Yes.
Okay. So good morning, everyone. Thank you very much for having me. It's a pleasure to join this seminar series, and I've really a high expectation that we could strike collaborations with the researchers in China and Far East. I'll be talking about high efficiency in photodetectors and how we can control photons and eventually use them for advanced level of imaging. This work is a collaboration between my colleagues in biomedical engineering, electrical and computer engineering in medical school, and we have Professor Laura Marco, Zeding, Xian Wang, and myself and our group members involved in this work. So let me talk a little bit about the life of photons. Photons are born mostly these days in semiconductor. If we want to talk about useful photons, photons such as laser photons. They live in dielectric materials like light guide or waveguide. They also die in semiconductor and they give birth to electrons and holes. And we then detect them in terms of electrical signal. And that's how detectors work. They're massless, they're quantized energy, they have wave particle duality, and they don't have any charge. And we all are familiar with that. And photons can be bent if we bring a very massive object close to them. Here you're looking at two galaxies. Between them, photons go, and then galaxies' gravitation changes the space, and the curvature contributes to bending of photons. The bending is happening in very large scale, millions of miles. We can't really make useful applications based on this kind of large dimensions, but we can bend photons in the lab in extremely small dimensions, such as micrometer or millimeter. And that way, people develop techniques for taming photons, manipulating photons, controlling them. And this is diffraction pattern, as you can see, that allows us to separate color of light. And that really is very helpful in finding the color of photon or identity of photon. And based on these diffraction patterns, we came up with a lot of interesting applications such as imaging devices, CD, DVD. We have fiber optical communication links. We do imaging and photography, spectral analysis, a lot of hardware security, and photons are used in so many things. This is really a big part of our life. So when people try to sense a photon and sense the identity or color of the photon, the way typically they would do this is they would use a big spectrometer. The photon light would be then split into different color. And the instruments that we typically use for this kind of work are large in dimension, because large path allows us to separate the colors separately, very distinctly. And in all these cases, we don't talk too much about making them fast. As long as we find the color, there are a lot of interesting applications we can explore. But people these days not only need to find the color of photon or detect a photon, they also need to find the lifetime of a photon. If a photon is super fast, it comes and it disappears. We need to know how fast its life is. And molecules, when you excite them, would also emit light to us, and we need to know what the lifetime of all those excitations are. So here is one example where you see on the left side of the screen, we are illuminating a sea creature, which under the illumination is giving us light back. So we are illuminating with, let's say, blue color. It gives us green and other colors. And there is lifetime of all these emissions. It's almost like on the right side, I'm showing some figures where someone is jumping up the wall, and there is a finite time we can stay there, up there, because at one point we'll lose our energy and will come down, and that's called lifetime for a photon. So for sensing molecules or modern day sensing, we not only need to find the color of photons, we also need to find the lifetime. We also need to do it efficiently, because a lot of sensing applications don't have too many photons. So we might have one, two, or few. So we should be able to detect light when there is only few photons there. And then we also need to do it real time, fast. Basically, we need to make sense and decision real time. So photons, detecting them needs to also lead us to right decisions. So there would be need for processing the data. So sensing at the moment is very important, and miniaturizing all these capabilities is extremely helpful, because that way, if we are talking about biomedical application, we can put all the instruments at the tip of an endoscope or a catheter. And this is something we explore in our group. So here I'll show you one particular application where you're looking at number of doctors, mathematicians, computer scientists, and my colleagues in biomedical engineering and electrical engineering are coming together. They're looking on the right side at the tumor, brain tumor. And then when you illuminate this tumor, on the left, it's a throat cancer. When you illuminate all these tumor tissues, you also get photons back, light back. And if you can detect the color of those light that our tissue emits, and if you can also detect the lifetime of all those photons, then you can very nicely find the margin or boundary of the tissue, good tissue and bad tissue. And once you do it in real time, robots can very smoothly easily go and remove all the bad tissues, cancer tissues, and that way the real-time surgery can very quickly identify the cancer areas and remove those areas. What do you need in this case? You need the capability to detect the light color. You also need the capability to detect the lifetime of these molecules that are bad, and their lifetime is typically in the range of nanosecond. So you need fast detectors, and you need really, really high quality, capable sensors that know what the wavelength is. So what do you need in modern day sensing system? You need ultrafast detectors. You need to integrate them in a large scale system with sensors, electronics, amplifiers, analog to digital converters. You need to miniaturize them. And if it is really capable of having internal gain, then if the photon numbers are small, we can amplify the signal. If we can reduce the noise, that helps. If we can reduce the crosstalk between different photon sensors, that also is very helpful. These are all the topics that in my group I work on, and my focus is to make all these things using silicon and silicon-like materials so that foundries can miniaturize them, make them low cost. So let's talk a little bit about the high-speed, ultra-fast photon detection. One application is probably very, very well known to everyone, is the fiber optic transceiver. You might have those in your office, you might have those in your home if you are bringing fiber to home. So in a transceiver, there is a transmitter, which is laser, a receiver, which is a photodetector, and then a lot of circuit elements, high-speed electronics. All these are made with either silicon or non-silicon material. So transmitter is laser. Silicon cannot really do a good job with lasing. So we use a non-silicon 3.5 material. In the photodetector or receiver, we also use a non-silicon material because the silicon's absorption capability is not good. Silicon is not fast. And then the rest of the circuit elements, all the mechanical part, electrical part, electronic circuit, all these are very made with silicon, and they're very low cost. So you have two expensive units. One is transmitter, one is receiver, because they're non-silicon. Now, can we make silicon fast and not use 3.5 material for detector? This is what exactly is my focus. So when we talk about a fast photodetector, you basically need a photodetector which is very thin in its active region. I'm showing a detector on the left, and that detector, when we illuminate with light, it's really quick because its positive and negative terminals are very close to each other. But if we decide to use a thin and fast detector like that, the absorption region is very thin. It basically doesn't absorb all the photons. So if you have 100 photons, maybe 90 will not be absorbed. Although it's fast, it's not really very useful for many applications. On the other hand, if I want to absorb all the photons, I'll make it very thick, like this one at the bottom. But a thick photodetector is not really a fast photodetector. It's slow. And slow photodetector cannot be made fast unless we make it thin, which makes it low in efficiency. So the material that you see here in the middle of this slide, it shows gallium arsenide is fast material, but gallium arsenide is also very expensive material. It has high mobility, but its mobility high, but its cost is also high. On the other hand, silicon is low cost. Right here, the cost of silicon, we know it's low, but its speed is also very slow. Its mobility is low. On the right, I'm showing some absorption curve. Silicon absorption curve is shown here, which looks lower than gallium arsenide or germanium or indium gallium arsenide and other material. So silicon doesn't absorb light very well. Silicon is not fast, and this is a problem. How do you overcome this? If we want to really use silicon in 5G, 6G system, if you want to use them for 100 gigabit per second or higher speed, you really can't use silicon in the current form. And if we want to really make things low cost, like connections between computers, connection between board to board, or connection between modules or within chips, you really need to use silicon effectively so that it's foundry, CMOS foundry compatible. Also, it's low cost. And right now, silicon is not really there. The cost right now is like $10+ for a computer-to-computer connection, but people are trying to make that less than $1, like $0.50, which requires reducing the hybrid integration that we currently do with gallium arsenide and other material. Also, people demonstrated that silicon electronics can be really fast, 400+ gigahertz. But silicon photonics is not that fast, because if we want to make them fast, we end up with losing efficiency. It's like 1% in the photodetector efficiency. So how can we have very fast electronics and very fast detector, but also very efficient, is what I do in my group. And why do I do that? Because silicon is ruling the world with CMOS technology. If we can make it fast and sensitive, it definitely helps in enhancing silicon capability and take it to the next level. And there are a number of applications that require low light, like biomedical imaging, LiDAR, and then a lot of biophotonic applications where one photon or few photons should be available. And there we need to really do a good job in enhancing efficiency. So now I'll show you what exactly happens when you illuminate silicon. Let's say I gave you 2-micron thick silicon that you see here, and you want to illuminate it with light from top. And the light wavelength is 850 nanometer that I'm showing here. 850 is a useful wavelength for a lot of applications, including data center or communication. So with a 2-micron thin silicon, I can make a fast photodetector, but I end up with only 10% efficiency. So out of 100 photon, only 10 would be absorbed. which is not really good, especially when there are only few photons, like 2 photons. I may end up with no absorption at all. So what people did in solar cell communities to enhance the efficiency of silicon absorption, people started generating this kind of surface texture. And this surface texture basically takes your alpha and makes it a little bit higher alpha or enhanced alpha. And solar cell community benefits from this by suppressing reflection, also by enhancing the material and light interaction. And Professor Ilya Blonowich, right here, he did some calculation and showed that if we do a good job with all this surface texturing, our alpha can be enhanced by a factor of 4n square. And what is n? N is the index of refraction. N square is basically the dielectric constant or permittivity that silicon is around 11 point something. And so alpha is enhanced quite a bit by a factor of 4n square. And if you do a really good job, your silicon photodetector, silicon solar cells get enhanced. So if we do nothing to silicon, silicon's alpha is very low. So here I'm plotting alpha right here. But with 4n square, you increase the efficiency with surface texture. But modern nanophotonic texturing technique that I show on the left, a group at Stanford, Professor Shanhui Fan is the PI. He showed that good nanophotonic techniques can actually enhance the efficiency from 4n square to much higher level. It can be 12n square. It can be even more. And you can increase it further to from 4n square to almost like 100x, 120x. So modern nanophotonic technique can make silicon 100 times more powerful in its absorption capability, which is what then can help you in making very, very fast photodetector and also very, very efficient photodetector. So here I'm showing some of the nanophotonic surface texture. These are photonic crystal. And if your photonic crystals are designed with a periodicity which is close to the wavelength of light you're interested in, then you end up with generating lots of guided mode in silicon. If your surface texture is smaller in periodicity compared to the wavelength that you see here, then you end up generating a band gap. We call it photonic band gap. So if I choose the first option, then I'll be able to bring in light to silicon and then create loss of guided mode. Basically, light will come from top and light will remain in material for a long time. So here, this cartoon shows if I start with a 30 micron silicon and illuminate it, light will keep going, and still many photons will be unabsorbed. But if I have this surface texture, even with 2 micron thick silicon, I can have loss of guided mode going into the silicon thin layer, and those will remain there for a long time so that we can absorb them efficiently. So here is a video that shows how this concept works. You are looking at the light propagation. On the left, light is coming from top. On the right, I'm showing the cross section. As light came from top, it started going down, and after around 15 femtosecond, light reached the bottom of the thin film, and it doesn't go to the bottom to the downward direction anymore. It keeps going to the lateral orientation, which gives us more time to absorb it. So here still the time shows around 30 femtosecond. I need around 40, 50, 60 femtosecond to absorb all the photons. So when I do that within less than 100 femtosecond, I am capable of absorbing most of my photon using a very thin silicon, which is 10 times, 20 times thinner than silicon, regular silicon. It's not only us who are doing it. In nature, you will see this kind of capabilities all the time. And I would show one example from nature, which is this begonia plant. They are typically in the forest under the big trees. They don't have too much of light coming to them. So they developed a nice technique, photonic crystal based technique. What you see here is inside their plant leaf. So light comes from top, and because plants are very interested in red light, so all these surface textures allow red light to efficiently get absorbed, which then turns into their food, and then the blue light gets reflected back, which is not really useful for the plant. So they optimize their absorption for a particular wavelength, which is what we also do in our photodetector. And if you look under scanning electron microscope, you will see this kind of photonic crystal or one-dimensional diffraction pattern, you can say, which allows this plant to absorb more and more photons. We developed two-dimensional or higher order diffraction patterns, which allows us to bring light from top and then spread it in many different orientations. And that way, interaction time increases and we absorb them more efficiently. Here, number of different kind of photonic crystals are shown. We call them light trapping or photon trapping structures. And they're created by using etching technique, dry etching, wet etching, and number of different dimensions and periodicities are used. And we saw that if we only have one hole like this one, we have very little improvement in the efficiency. But if you want to improve it more and more, then you need to increase number of holes. So here we have 2 and then 4, 10. As you can see, the efficiency is going up higher and higher. As we increase the number of holes, like 30 holes gives us really, really high efficiency, like 35%. Whereas with no hole, we get 10%. So what that means is out of 100 photons, your regular photodetector would only absorb 10 photons. But in our structure, we can absorb more and more as we increase the photon trapping hole numbers in the photodetector. So what exactly is happening is shown here. A regular photodetector that you can buy right now will not have this kind of surface texture. And the light velocity in that regular photodetector is shown here in this blue curve, which basically is roughly around 30% of the velocity in free space. But then you want to slow down the light. So with all this surface texture, we are suppressing the light velocity by quite a bit, and it comes down to the 10% level compared to the vacuum. What that does is it gives you more time to absorb your light, which is what we need, because silicon is really, really bad in absorbing photons. And if we do a good job, we actually can very effectively absorb photons. So theoretically, at 850 nanometer for a high-speed photodetector, I can only absorb 10%. But then if I do a good job with my design, I can actually increase it from 10% to almost 95%. We in the lab demonstrated like this. So light here is coming from top and it keeps going in all these different directions, and you absorb the light because of prolonged interaction that is happening in the material. So here with silicon, we showed around 86% efficiency, which improved all the way 10% from 10% to 86%. With germanium, we implemented this and we saw that germanium is already good as an absorber. But if you want to make a fast device, we make it thin, and thin germanium photodetector would be low in efficiency, such as 47% that you see here. At 1550 nanometer, we increased it to 73% in our case. And that basically makes your device fast and also makes it high in efficiency. We didn't do too much of work with germanium, but we tried to implement our device, silicon device, in system experiment. So silicon typically is not used in systems such as 50 gigabit per second or 100 gigabit per second because they are not as fast. And when you design something with such high speed, their efficiency suffers quite a bit. In our case, we saw that their communication capability is very good, even with 50 gigabit communication. So this is what I published in Advanced Photonic Nexus, which basically says your regular silicon has an alpha or absorption coefficient that we show here right at this level. If you want to increase it, take it above gallium arsenide and to the level where indium gallium arsenide is, which is really, really a good material for photodetection, or take it to the level where germanium is, you need to use this kind of light trapping structure. So alpha increases quite a bit by this kind of light trapping structures that you add. Just like us, a number of commercial entities such as Sony, OmniVision, ON Semiconductor also added this kind of light trapping structures in their imaging sensors. In fact, those are in your phone now, in your phone camera. So this kind of light trapping structure basically expanded their infrared efficiency, and then some of the visual efficiency also got improved, as you can see here. And the pixels, when they're thinner, you also have the capability to make them fast. And a lot of these kind of sensors need to be need to operate at higher frequencies or higher speed. We demonstrated this with PIN photodiode in 2017. Stanford group led by Professor Jim Harris demonstrated in avalanche photodiode. A few months later, a couple of months after us, and then recently University of Virginia and UT Austin collaborated, and they demonstrated similar kind of structures for materials that are longer wavelength capable, such as 2 micron or more. Now, this is really a good technique to enhance the light absorption capability when you have 1, 2, or few photons, but and then you can make them fast. Can you do something else? Can you add other capabilities to miniaturize your system? That's what we looked at. So imagine we designed photo sensors with different kind of light trapping structures. And I showed you, we tried many different structures in our lab. As you can see, they are shown here with scanning electron microscopy imaging. And if your dimensions, periods, and whole shapes and size change, they would look different. So here, under optical microscope, you can see these detectors are different in their characteristics, color, which basically means they're reflecting different color of light from different sensors. Now, if I want to now turn this into a spectrometer, I can compare it with a traditional spectrometer. And what does traditional spectrometer do? They have light, and that light goes through a collimator, and then eventually that light goes through a prism or grating or monochromator, which then separates the color. And those color then eventually are used to understand what exactly you are sensing. Now, all this extra hardware that you see here can be removed if I simply decide to take a sample and I illuminate it directly with light. In the previous case, what you do is you illuminate it with individual known light, and then your sensor registers what you see from the sample is coming. But here, we directly illuminate our sample with light, whether it's biotissue or some kind of chemicals, and then the emitted light from the sample is collected by the photodetector. Because they are all designed to have different kind of characteristics, now you just need an algorithm to figure out what kind of color the sample is emitting. This is demonstrated by another example here. Imagine you have many different detectors. They're all designed with different characteristics. So here is one detector characteristics. Here is another one. Here is another one. And then all these different, the intersections here are basically all individual detectors. If you now test them and then train them, if you know how they behave under known light, then you can expose these detectors to unknown light, and then the detector will tell you through an algorithm what the color of that unknown light is. Another group showed here that a imaging sensor can be covered with some filters, different filters in different regions. And then once you know what the characteristics of these sensors are under known light, you can now expose them to unknown light. As you can see, these filters are all created with different kind of features. In our case, filter is already integrated in the photodetector, but here these people integrated a layer of filter on top of an imaging sensor. All these help you in generating your unknown light profile. So in our case, we used many different features, as you can see on the right, to create all these sensors with different characteristics, and they now are all unique. Under same light, they behave differently. Once we figure out how they behave by exposing them to known light and by measuring how their behavior is, now we are ready to find unknown light. And in that activity, we just need an algorithm. So here you're looking at this very high speed sensor, which is illuminated and the photons are collected. Each of the sensor pixels will be designed differently. They are small, they are ultra fast, they are made with silicon, and they are capable of now resolving the color of photon. Also, because they are ultra fast, they can very efficiently find the find the lifetime of the photon, or can find how fast photons are. So we are envisioning doing it at extremely high speed, like 100 gigahertz, increasing the efficiency by about 90%. We integrate it in CMOS. We are also thinking to make the noise low because we are reducing materials, which means the noise coming from the material would be low. And this is very wide spectral. I showed you a number of profile of our absorption that are really, really broadband. And this is scalable and mass manufacturable. So I mentioned about creating photodetectors that are different. Now, looking at the photodetectors, you can see the images show they are different. In fact, if you look at their efficiency or external quantum efficiency versus wavelength, they all are different because they're designed to be different. And to convince yourself, you do something else, which is wavelet transform. What it does is it basically says how unique each detector is. And that's really important because we develop an algorithm based on unique couple of detectors, detector 1, 2, 3, 4, 5, 6, 7, 8, and all of them are very uniform. So you have uniform detectors. They are capable of absorbing low number of photons. They are also very fast. That is what you need to reduce your hardware and miniaturize everything. So a group from Italy actually demonstrated a very nice such a system where they used 18 photodetectors. They're all different, very unique in their characteristics. They also chose them to be fast, and they found that they can find the spectrum or color of light. They can also find the lifetime of the photons, which is important. Once you know what the lifetime is and the color is, you can very distinctly figure out what the molecule is. And once you know what the molecule is, the application can be your cancer margin detection. The application could be your finding molecules that you want to find, or sensing something that is not easy to sense simply using the color of light. Many molecules might emit the same wavelength, but the lifetime in all these cases could vary. And that way you can identify molecule by using two unique parameters. One is the wavelength and another one is lifetime. So what we exactly do in my group is we try to enhance the efficiency of photons, and that makes our detectors very, very efficient. And we developed a technique to make the detectors very thin, still absorb a lot of photons, which makes them fast, because thin devices are fast, small devices are fast, but small and thin devices are not good in a traditional way to make them highly efficient. We do that. But then because we are creating all these surface textures, we can now make all these detectors capable of becoming unique. And once they're unique, we can then figure out how they behave under known light. Once we know how they behave under known light, we then develop a matrix which allows us to then find an unknown spectrum. And because they're designed to be fast, they can find the decay time or lifetime. So what is possible in a situation like this? You can take a number of silicon sensors, light trapping sensors that are fast, that are highly efficient, and then you can integrate them with all kind of electronics, all kind of amplifiers, A to D converters, readout circuitries, and whatever is needed to build an imaging system. And because it's in silicon, it's super inexpensive, it's foundry compatible, and the system that currently people have, which can do the same kind of imaging, are way more expensive. We're envisioning this to be miniaturized and eventually be able to sit at the tip of an endoscope tip. So that way, AI algorithm plus all these AI capable sensors and their capability to absorb extremely small number of photons and their capability to operate at very high speed contributes collectively to AI-driven ultrafast sensing and imaging. And here, photon manipulation remains behind all these activities to offer this kind of capability. I'll stop here, and if there are questions, we can briefly answer those now. Thank you very much for your attention.
Okay, thank you very much, Professor Islam. And so now we can take questions.
Will I be able to see questions, or will you ask?
I will probably have to translate because much of the audiences are Chinese researchers. Sure. They may find it a bit daunting to ask questions in English. So, sure. Okay. So, yes, here we have the first question. Silicon is, is transparent for wavelengths beyond 1200 nanometers. So, can you use the photon trapping detectors for optical communications at 1300 and 1550 nanometer wavelengths?
Very good question. This is a valid one because we can't absorb light beyond actually 1.1 micron or 1100 nanometer. So here I'm showing a germanium on silicon. This is basically a thin layer of germanium, and germanium can take you above 1100 nanometer. You can go all the way up to 1700. It's true, silicon will not do any kind of absorption or sensing above 1100 nanometer, but silicon below 1100 nanometer has lots of applications in data center and others where you can make them really absorb very well even at 1000 nanometer or 1050, 1064 nanometer. Okay. Beyond that, when you are above the cutoff wavelength for silicon, you have germanium. And I showed another work from a group where people used a 3.5 material, like this slide. Am I sharing? Actually, I stopped sharing probably. Or do you see my screen? By the way?
I can see your screen. Yes.
Okay. So here I'm showing photon trapping, avalanche photodiode, mid-infrared application. People decided to choose some long wavelength infrared material also to implement this approach. But it's true, silicon would not do much for beyond 1100 nanometer, and there you need to choose another material. But then without light trapping structure, they will not do a good job, and people decided to explore photon trapping in germanium and similar materials. Even indium gallium arsenide, which is really widely used for longer wavelength, infrared wavelengths, people explored photon trapping and made them very fast while also very efficient.
Okay, good, great. So here is another question. What about the optical bandwidth of the photon trapping? Because photonic crystals are periodical structures, and sure. would it only work for a narrow range of wavelengths?
Yeah, very important question. So let me quickly show this slide here where we are showing some simulation results, which goes between 800 to 900 nanometer. As you can see, it's fairly wide spectral. It's not narrowband like photonic crystal or a resonant cavity enhanced kind of interferometric detectors. We also show data where we start from 800 nanometer all the way to 1600 nanometer. So this is, and as you can see, the enhancement is fairly good. These green dots and blue dots are showing our devices, and they are showing pretty broad band in optical bandwidth. You can, for the application that I showed close to the end of my talk, where I was trying to make unique photodetectors for an array, small array. Here on the left, you are looking at the detectors that we deliberately designed to have high efficiency for some wavelength, low efficiency for other wavelengths, because we wanted to make them different from each other. But if your goal is to make them very wide in spectral response, optical spectral response, you can make that.
Okay, thank you. So here comes another question. Is it how sensitive is the device to fabrication errors? The holes do they have to be always the same size, or if a small variation in the shape and the size of the holes does it affect the sensitivity of the detector?
This is a very good question, and I clearly see you have some experts in the audience. This is really not an issue because, as I mentioned, our photon trapping structures need to be in the range of the wavelength to effectively contribute to light trapping. So if your wavelength is, let's say, 1 micron, your photon trapping hole period needs to be 1 micron roughly. Now, will it work if it is 1.5 micron? It would be perfectly okay. Your efficiency might go down or go up a little bit. Will it work if it is 0.2 micron? No, because then you become photonic band gap material. Okay. So you try to avoid that kind of big fluctuation, but typically microfabrication variations are not really that bad in modern technology. So when we design devices with, let's say, 700 nanometer light trapping hole diameter, we saw 50, 100 nanometer variation or some deformation here and there doesn't really contribute to any difference.
Okay, so yes, if we go back to page 24, the band gap diagram, right. The band diagram, is it because we have a lot of states distributed in a wide range of energy or a wide range of in the vertical direction over on the top?
Right.
So
exactly,
it doesn't matter which line you are on, almost, right? Okay.
Also, I could show this one. So here, I didn't explain too much, but with the black little dots, I'm showing many modes that are generated. Some of these modes are faster than the regular speed of light in silicon, but most of the modes are very slow. Some are extremely slow. So you're creating so many modes, and a little bit of variation creates maybe a little bit different mode, but they all remain
other modes. Yes, indeed. Yes. Okay, great. So another question. You have to etch through silicon, and then this increases the surface area of the silicon, and would that result in increased surface recombination, and how would that deteriorate the performance?
Very important question, and you always would worry about any kind of leakage current or any kind of recombination because of the damage you are causing on the surface. So in our early days, we found suddenly the leakage current or recombination would increase by 3, 4, 5 orders of magnitude. And then over time, we learned how to passivate the surfaces. And if you are using silicon, one good technique is to simply coat it with hydrogen passivation or hydrofluoric acid dip. Or you can grow a little bit of oxide all around these holes by doing a couple of nanometer oxidation. And that basically takes care of all these surface damages. We also tried removing a little bit of silicon by wet etching. So that removes like 10 nanometer of silicon, and that makes the surfaces much better in quality after the RI and all those damages are done. And then small passivation step like hydrofluoric acid dipping would give a very long-term passivation, surface passivation.
Great. Another question, which is about the spectrometer. I think it's about the spectrometer. Yes.
All right.
In one of the pages, I think is in page 45. Yes, you showed the different response of different pixels in this graph, and so you then use a algorithm to reconstruct the spectrum according to the different response of the different pixels. How, some of the curves are quite close to each other, only slightly different, and how different they need to be in order to have a good performance.
So they look different. I mean, they look similar. Some of them are quite similar to each other. So to show you that they're actually not that similar, I'm using this wavelet transform. We picked 8 devices for a particular experiment. Actually, some of these curves here are similar because the devices are also very similar. So you can see some of the colors are also very close to each other. And they are not really best candidates for this kind of spectroscopic reconstructive imaging. But if you allow very distinct 8 or 10 or 12 detectors, and if you now want to see how distinct they are, wavelet transform actually does that. So here, all these wavelet transform are looking very different from each other. They might look similar, but there is microscopic differences for different areas, which will contribute to making them very distinct, and your algorithm then works very well.
Okay. Any more questions? Okay. Yeah, it looks like we don't have more questions from the audience, and so if that's the case, look, yes, okay. So okay, if that's the case, let's thank Professor Islam again for this fascinating talk, where he showed that it is possible to enhance the response of silicon photodetectors using surface structures very significantly for more than 1, even 2 orders of magnitude, and this allows to construct photodetectors with very low cost fabrication materials, and which is also compatible with standard silicon fabrication foundry technologies, and doesn't require the integration of other materials such as indium gallium arsenide. And also on the other dimension, he also showed that by placing nanostructures, different nanostructures on different photodetectors in a detector array, it is possible to use to discern the wavelengths or the spectrum of the light using the different responses of the different pixels, and so therefore to reconstruct the spectrum of the light, which is I think is at the moment is a very hot topic, and because small light sensors that are sensitive and low cost, and be able to have spectral resolution clearly enables a very wide range of applications, both in the industrial environment and also in a sort of like a personal or customer applications such as health and the environment and so on. Yes, so let's thank Professor Saif Islam again for this fascinating talk, and that should be all of the contents today. And thank the audience for their attendance and their questions. Thank you, Professor Islam.
Thank you for having me, and greetings from UC Davis. We look forward to having some of you here.
We hope to be able to have more submissions of excellent work from your group to both Advanced Photonics and Advanced Photonics Nexus. And yeah, thank you again.
Thank you. Very good night. Bye-bye.
Thank you. Bye-bye.